questions overall from some previous test of video. So I try to choose ones that will be like somehow relevant, you know. So, yeah.
Can I ask a question? We talk about about JR, and we took R to infinity, and we saw.
Talk about the long range interaction.
Yes.
Okay.
And we saw that if sigma is larger than 2, then there is no phase transition, and if it's less than 2, it's and equal to 2, there is a phase transition.
Okay.
And in the test, I saw that they took one M בריבוע, ואז הם פשוט לקחו את זה לאינסוף, בביטוי של ה-J, ואז הם, אם זה אינסוף, אז הם אמרו, יש המעבר פאזה, ואם זה 0, אז אין מעבר פאזה. עכשיו, בגלל שזה יותר מהר דורך ל-0 מאשר 1 חלקי M בריבוע.
אוקיי.
אז עכשיו, כאילו אנחנו ראינו את זה שאנחנו פשוט לקחנו את ה-R לאינסוף, ולא חילקנו את זה בעוד איזה פונקציה.
Yeah, like, okay, what we did, we say we have something that go like that, and then we find condition of sigma, and we found that like the critical sigma is 2, and so you can take the expression of J of R and take like Taylor series or something, and find that sigma and say if it's larger or smaller than 2, or you can like divide or multiply it by like m squared and then see like how that's go. Like it's just equivalent. So let's go to the questions. I'm not going to have so much time in the end of the tutorial for like other questions and stuff like that. So if you have stuff like, you can write to me and then I come to the office or something, just because you know today is today and we don't want to die from rockets or something, whatever's going to happen. No, I'm joking, just because of the fast. So okay, so the first question is about transfer metrics. So this is from the last year, from 2023. Moed Aleph, question 3. So we solved like a similar question in the tutorial. We have different Hamiltonians, and the question is, for each Hamiltonian, what's the minimal size of the transfer matrix? Okay, so that's fine. Okay, so first one, the Hamiltonian is equal to, this is like a Potts model. We have minus J, sum over I of, so we have delta of sigma I with sigma I plus 2, plus delta of sigma I with sigma I plus 3, where sigma I go from 1 to until some q. So we know that it doesn't matter if it's Ising model or Potts model or what's the nature of the interaction. What matters is that we have interaction between sigma I and sigma I plus 2 or sigma I plus 3. So we have like, if this is the one-dimensional system, so this is I, so it's going to interact with this one, I plus 2, it's going to interact with this one, and with this one. So what's going to be the minimal size of the transfer matrix?
כאילו זה 4 על 4.
Q בחזקת 2.
So
Q בחזקת 3.
yeah. So as we said, we have the number of possible values for sigma. So in that case, it's going to be Q. So number of states. This is going to be to the power of the size of the block. So this is block size. Of course, multiplied by the same size of the same thing. So in that case, we're going to have we have Q because this is the number of states, and the size of the block is 3 because we interact with 3 spins forward. So this is Q to the power of 3 multiplied by Q to the power of 3. So this is going to be the minimal size of the matrix that we need to describe the system.
זה בעצם הסיבה שככה האינטראקציה שלנו תהיה מקסימום בין שכנים סמוכים.
Yeah, so define the block with that, so you only interact with like the block next. Okay. So that was the first. Okay. Number 2, the Hamiltonian is equal to. So this is Ising model. So we have sum over SI with SI plus 11 plus SI plus 19. So this one is the same concept. It's even easier. We have SI can only be plus or minus 1 unless someone says something else. This is the Ising model that we know. So we have 2 states for SI. And we have the size of the block going to be 19 because we have 19 this interaction, like the farthest interaction. So we have 2 to 19 multiplied by 2 to 19.
שרק נמצא את המינימה, או גם לבטא אותה?
כן, הם רוצים במבחן שאתה עושה למצוא את 2 בחזקת 19 או 2 בחזקת 19.
What did you? If you need to find the matrix?
לא, ברור שלא. לא, בקלים זה משהו יותר פשוט.
What did you ask? If you need to find the matrix?
כן, אם זה משהו יותר פשוט, לא כמובן 2.
You can get a question, find the transfer matrix, but yeah, it's not going to be that. It's going to be something simpler, but sure. That's a possible question. But I chose to solve this question. So number 3, the Hamiltonian is equal to minus j. This is also an Ising model. So now we have, like it says in the question, that we have kind of 2-dimensional system. So we have 2 lines of spin. So we have like 2 like Ising chains. So we have something like that. So we have end spin to that direction, and we have two lines. So when we write the Hamiltonian, we're going to have SI1. So this is going to be the coordinate for the x direction, and this is going to be the coordinate for the y direction. So this is kind of like x and y. So SI1 with SI2 plus, yeah, I shouldn't have put it here. Okay, I could just continue to write here. Plus SI1 with SI plus I plus 1. So SI1 with SI plus 1, 1. SI2, SI plus 1, 2. And SI1 with SI plus 3, 2. So yeah, so it's kind of 2-dimensional because you only have 2 work. So
X and Y.
so so we have interaction of I1 with I2. So this is just all of those. We have interaction of I1 with I plus 1 with I plus 1, 1. So this is all of those. The same with that expression for the second row. And this one is the one that's like somehow more interesting. So we have I1. So it's this one, for example, with I plus 3, 2. So it's like 1, 2, 3. This one. And the same with this one. And we don't have more rows, but
אז סך הכל
you
6
understand.
איברים. 2 ו-6. אז זה 2 בשישית ו-2 בשישית.
2
Yeah,
כפול 3.
so the minimal block going to be now this one. So you see that like in the x direction we're going to have 3 neighbors because this is the farthest interaction, and we have to take the 2 columns because it's not symmetric. So we take a 6 since block, and SI as usual is have 2 states, so we have 2 to the power of 6 and 2 to the power of 6. And the last one.
אפשר לציין.
Question?
איך מנמקים? מספיק לנמק על פי המספר המצבים בחזקת הגודל הבלוק? זה מספיק או שהוא רוצה יותר?
Yeah, like I think like the most minimal explanation is enough. You can do like that drawing to show that you understand how it looks, and like yeah. It's enough.
Tanya, the block have to be that way, or you can shift it by middle?
Yeah, you could also look that as a block. Like it doesn't matter. It just keep here and here.
כאילו מה שצריך להופיע בתוכו זה מספר האתרים ומספר הקשרים המינימלי כדי לסמן אותו כשאני בא לסמן את הבלוק אני צריך לדאוג שכל הקשרים מופיעים בתוכו וכל המינימל סייטים, אתרים.
Yeah, like you can always think.
כי תמיד אני מתבלבל פה בסכום הזה.
If you get confused, you can always go back to the most basic model of like one dimensional Isaac chain, and you're like, oh, I have interaction with SI and SI plus 1. So like this is the minimal one that I take because like and then I have like interaction between this block and this block. So here I have, if I take like this one, like I cannot, this one is too far away, so I need to keep interaction between I and I plus V. Like I need them to be like
כן, כמו מספיק פשוט
nearby.
שאלה. אני אומר שנגיד תשובה, אז מספיק להגיד רק פשוט שהתשובה תהיה פשוט 2 חזקת 6 כפול 2 חזקת 6, כאילו לא צריך יותר מזה לנמק או משהו?
Yeah, you need to write some words, like to say like, oh, I have like 6 spins block and two states for SI, or do like, or just if you just put that and then write that, like he can see that you understand. You know, but you need to give him something.
כאילו נגיד למשל שאני שים את התשובה, אז לקחתי את הכל, ו-X אני יודע שחלקוס כאילו 3, אז כאילו עם זה אני מגיע לזה של 6 דברים.
Yeah, like very. Okay, and the last one that's like kind of similar to number 3 actually. So this is minus J. So here we have also like 2-dimensional system, but instead of x go from 1 to 2, we have x would go up to 6. So we rewrite it with 2 summations. So this one, so we have I that go from 1 to n as usual. I never write like what I is, but you know. And inside the bracket we have one summation of j. This is going to be like the y coordinate that go from 1 to 6 of SI j with SI plus 1 j, and this is plus sum of, so this is also j. J go from 1 to 5. Sij plus 1 plus Sij as I plus 3 j plus 1. So how does that look? So we have 1, 2, 3, 4, 5, 6. Okay, so we have interaction of I with I plus 1 for each value of j. So this is going to give us all of those. So for j equal 1, j equal 2, j equal 3, 4, 5, 6. And then we have interaction of each spin with the spin above it. So we're going to have all of those. So this one is go only to 5 because we go to j plus 1. And the last one, it's always the most interesting one. We have ij with I plus 3 and j plus 1. So we go from this one, we go to j plus 1, 1, 2, 3. So this, and this, and this. And the same for all of the spins, you understand. So, yeah, so this is basically the same as here. We have, I need more color. So we have 3 spins in the x direction, and all of the spins in the y direction, and this is going to be one block. So this is 6, 2, 10.
גם מה עושים במצב שאומרים שיש נגיד אתר מסוים שיכול לקבל ספין 1, 2, 3 ואתר אחר 1, 2, 3, 4? ראיתי שאלה כזאת.
So, okay, so if I have like a, so because what we say here, we have the number of possibilities for the spin to the power of the size of the block. So if we have like let's say like a 1D thing, and I think we did that in the tutorial, that we had like half of the spins can be like 1, 2, 3, and half of the spins can be 1, 2, 3, 4, or something like that. So so let's say like if you have only like the nearest neighbor thing, so instead of have yeah, so instead of have like 2 by 2 if it's normalizing, so now you have like 3 multiplied by 4 because like half the spin like that, half the spin like that. So overall.
עוד אחד קצת, לא?
No, okay, then there you had, yeah, but there you had interactions like that, right? Just remember the question. No, I think it's fine. Because for each block that you're going to look, like this spin going to have, right? Because we look at like what's the transfer matrix. You look at like transfer from sigma I to sigma I plus 1, if it's only like the simplest form. So sigma I going to have, so like this one going to have 3 options. So it's either like 1, 2, 3, and then sigma I plus 1 going to have 1, 2, 3, 4. So this is going to be the This is also from 2023.
איזה מועד?
The same one, the first. Wait. So this is question 2. So, given some general form of the free energy, so we have F equal A of T m square plus B m to the power 18 plus C m to the power 20 minus HM. So that's like Landau thing. So the first one is just so the first one is to find the critical exponent. And show that they follow the scaling relation. So this is beta delta minus 1 equal gamma. And then the second part of the question, you have like different forms of A and of F, and you need to say like if you have a second order phase transition, so you write it like after. So
לא הבנתי, צריך להוכיח את זה גם? זה מה שהם ביקשו?
no, you need to find the critical exponents for that specific energy and show that they follow that.
אוקיי.
So let's start with the easier one, that is B. Yeah.
Do we really need to remember all of the critical exponents?
Unfortunately, yeah.
Oh, okay.
Like if I think I'm going to be in the test. I don't remember when is it, but I think I'm going to be there. And like if you ask me, I'll tell you.
You mean the basic one that alpha is 0, beta is חצי, lambda שווה 3.
This depends on the model. This is for like normalizing model.
Yeah.
So yeah, so the critical exponents are basically those, and also alpha. And so I don't know if you don't meant in the question that you're also going to find alpha because it's not part of the scaling relation, but we're going to find it because why not? So okay, so to find beta. Yeah, so let's just write.
כאשר H שווה 0.
M go like T to beta, this is for beta, and go like H1 over delta, stability,
כן.
C בחזקת ממסד.
רגע.
לא צריך לשים ערך מוחלט?
Yeah.
אוקיי. גם
זה חובה לשים ערך מוחלט?
לפעמים. תלוי בשיר.
Like mathematically speaking, yes, but if you ask from like the test perspective, as so like I don't think anyone cares.
גם ב-H צריך לשים ערך.
Yeah, but yeah. Okay, so let's start with beta. So to find beta, we use the minimum of the free energy. So we take the derivative of the free energy with m for h equals 0. We compare that to 0. So this is going to be a of t m like 2m plus 18 d m to the power 17 plus something that's off order of magnitude of m to the power 19. So this is always going to be like negligible because we look near to the phase transition point, so m is very small. So we're going to ignore like the highest order. Like we only needed two first orders to solve it. So like this one actually never holds any information related to what happened on the critical point. And h equals 0, so that's it. Yeah, it's also given in the question, but this is always true that like a of t go like t minus t critical, and it's like change sign.
אפשר להגיד A כמו T הולך כמו T? A T גדול הולך כמו T?
T קטן כפול T.
לא, זה T גדול צריך להיות.
T קטן כפול T.
A T הולך כמו T קטן, וזהו.
T קטן כפול T.
כן, כן, כן.
Yeah. Sometimes it can also be like that.
Yeah.
That's also the same. Always the same thing. Okay, so this is equal to 0. So we have one solution that's like n equals 0. That's not interesting. And the other solution is a of t that's proportional to t. So t is proportional to m to 16, right? I divided those both by m. So that means that if m going to like t2 to the power beta, so m proportional to t1 over 16. So beta equal to 1 over 16.
שאלה, M שווה 0 ש-T קטן מ-0, נכון? T כאילו...
So what?
לא, שהוא גדול מ-0.
לא, קטן.
What is what?
קטן מ-0. M שווה ל-0 כש-T קטן מ-0.
גדול מ-0, אמרנו.
T קטן, כאילו, T קטן, קטן מ-0.
When t...
לא, T קטן, קטן מ-0.
פשוט פתרון, m שווה 0.
לא, הוא שואל לגבי מה שדיברנו בתרגול. אמרנו ש-T קטן, שהוא קטן מ-0.
כאילו, M שווה 0 ש-T קטן שווה 0.
הולך כמו T בחזקת בטא.
When this is smaller than 0, it means that t is smaller than the critical temperature. So you're in the low temperature regime, so you have so the magnetization is going to be like not non-zero. Like this is going to be like that part of the solution.
אז ב-T גדול...
Because remember, yeah, like
ב-T גדול מ-0 זה M0?
כן.
yeah.
אוקיי.
Because remember you have like the thing as function of temperature, so you have like stuff like that. If you look like it's like higher dimensions. Okay, so I'm just going to write it here for future use. So this is for beta. Now let's do beta. So this is the same, but now we take the temperature to be 0, the temperature. So t equals 0, which means that a of t is going to be 0. So now we have 18 b m to 17 plus O of m of 19, which is going to ignore. And now we're also going to have additional term from the magnetic field. So we have minus h. This is all equal to 0. So m to 17 is proportional to h. So delta is equal to 17. Right? 1 over 17. So that's it.
דלת צריך שווה 1 או משהו? 1
את האיברים, תראה שזה פשוט
Yeah, but delta defined like 1 over. So,
אפשר שדלתה שווה 17.
heat capacity.
אפשר שדלתה שווה 17. זאת אומרת 1 חלקי 17.
לא, אבל זה
לא,
אחד
דלתא
חלקי
זה
דלתא.
1 חלקי.
אוקיי, צודק.
דלתא S נגזרת שנייה של דלתא S ודלתא T.
So specific heat or heat capacity, I don't know.
D
this is the second
בריבוע.
This is the second derivative of
דלתא T.
sorry.
T.
This is the second derivative of the free energy with the temperature. So we don't have the free energy explicitly as function of the temperature. So what we're going to do, we're going to use the scaling of B of beta, and we're going to write this as so we have the second derivative of T, and we have A of T is proportional to T. So this is just T. M squared is actually T to the power 2 over 16. So this is 1 plus 1 over 8 plus M to 18. So again, T to the power 18 over 16 plus some higher orders.
גם פה H שווה 0.
So
גם פה H שווה 0. כאילו,
Yeah.
H שווה 0.
So this is it. So this is first derivative, we take the 1, the second derivative this, so this is like 1 over 8 minus 1. So so overall, what is positive? Minus alpha of that, so alpha is equal to 1 minus 1 over 8. I don't know why that's and we have the susceptibility.
T גדול מ-0 זה F של 0.
So
F לפי H.
T ל-DH, DF
זה השאלה אנחנו יודעים לו.
So, last one, the susceptibility. So we have the derivative of M over the magnetic field. So, as I showed in the tutorial, you have like more than one way to do that. You have a way that is more similar to the way that we found beta. Like you go to the free energy, the derivative compared to 0. But I like more the like the stupid way to do that, which is kind of like what we did here, but like you go from the magnetization to the magnetic field to the temperature. But you're welcome to use your own way. So the derivative over H of the magnetization, we know that M go like A to 1 over 17. So this is H1 over 17. So this is H1 over 17 minus 1. That's proportional.
מציגים את ה-M.
And from H, let's go back to M. So this is M1 minus 17. So minus 16. And from M, we go back to the temperature. So we said that M go like T to beta, so 1 over 16. So this is actually T minus 1. So the susceptibility go like T2 to minus gamma, so that means that gamma equal 1.
למה אבל בסוספיטביליטי אנחנו לוקחים, כאילו אנחנו מצמצמים את שתי איברים מסדר גודל גדול, חוץ מ-H?
No, this is No, I didn't look at the free energy at this calculation. I just used the critical
רק
exponent.
H
Like I
כאילו,
used
אז-
beta and delta.
כן, אבל ראיתי שפשוט מוחקים את ה-BM בחזקת 18 פלוס CM בחזקת 20. פשוט מוחקים אותם, ואז גוזרים את ה-HM בריבוע מינוס HM. למה אבל מורידים את ה-M בחזקת 18 ו-M בחזקת 20?
You
למה
only
לא רק
want
M
to
בחזקת
stay
20?
eventually with the leading order. So when we did, for example, the calculation for beta, you needed to keep like two terms because compared to 0, so you cannot just say, oh, this is equal to 0 and that's it. So you need to keep at least one order. You can always keep extra orders and then like see what you get. But or if you stack like too few orders, you're just going to get only the trivial solution, which is equal to 0. So you can always try. Okay. And of course you can put it here and see that it works. I guess it all allows calculators in the test. I don't remember.
Yeah.
That's okay. So they're just early things to not allow.
דף נוסחאות, אבל לא יהיה נכון. דף נוסחאות.
No,
רשום
there's
שהחומר העזר היחיד שמותר זה ספר אינטגרלים.
yeah.
אז רק מחשבון הפעם.
So that was just the first part of the question. The second part, we have different examples for the free energy. And the question is for each one of those examples, is the system like undergo a final temperature second order phase transition. So let's see. So the first one, we have F equal A of T. A of T is always the same A of T. M to the power 4 plus B M to the power 6 plus C M to the power 19.
Sorry, can you read question 1, you said? החלק השני.
Yeah, this is basically like
איזה
point
שאלה.
A.
Okay.
Yeah, sorry. This is all question 2.
Okay.
So this is like the first part of the question, and that's like the second part of the question.
צריך לומר אם זה עובר מעבר פאזה.
Yeah, and the question is, do you have a second order final temperature phase transition? So this is like a yes/no question.
תגיד שאלה קצרה.
Yeah.
לא בהכרח כעיקרון צריך להסתכל לראות אם הפונקציה סימטרית, אלא כאילו ראיתי דוגמאות שהם ממש עשו נגזרת ראשונה, נגזרת שנייה, ראו בנגזרת הראשונה שיש 3 מינימומים, נגיד 2 מינימומים ו1 מקסימומים, ואז בנגזרת שנייה הם ראו נגיד שהנגזרת עבור אותו היא שלילית, אז זה מקסימום, עבור אותו פיק אמצעי, ועבור שני הפיקים הנוספים, הצדדים, ראו שהנגזרת השנייה היא פלוס.
אוקיי.
כאילו היא חיובית, לכן זה מינימום, ואז כאילו עשו ממש פיתוח של הפונקציה ולא רק הסתכלו אם היא סימטרית.
Sure, yeah, you can do like we know basically how first order and second order phase transition works, like it relates to the continuity of the first and second derivative and how many minima you have and stuff like that. But like you don't have to, because in like part of the thing of Landau theory, like he kind of gives to you, he say like, oh, you have phase transition if the free energy follows 1, 2, 3, 4. So for you this is just you can explain that from like intuition point of view. So like for this example, for example, you have you have one odd exponent of m, so you know that it's going to look like something like that, for example. So you have something that's like very unstable, so you could just say that.
Okay.
But like
אני צריך להסביר איך זה נראה גרפית, או שמספיק להגיד שהתנאי נגיד ה-XYZ לא מתקיים פה, ולכן זה...
לנדאו.
yeah, I think you should say that like, oh, it's unstable, or oh, you like what does it mean that you have an odd order? Because if you have an odd order of that one of the that exponent is not going to be the same if you have an order here. So you need to say like in 2 words, like what does it mean? So so we're going to see soon like another example for that. But like here, for example, you have something that's going to be unstable. So just say it's enough. Also, like this is a very general flow. Like nothing looks like that. I'm just.
רגע, אז ב-M19 כאילו זה פשוט לא יציב?
Yeah, like you usually have something that's like,
לא יציבה?
if you look like below or above the critical temperature, so you have something that's having one minimum point, and let's go to something that's have something like 2 minima. So what's happened if you add like some odd terms to that? It just breaks the symmetry, make everything go to that.
אם החזקה של 19 הייתה נגיד איפה שהשש, נגיד זה היה M ברביעית, M בחזקת 13 ו-M בחזקת 18.
So it's still going to break the symmetry.
אותו דבר זה, אוקיי.
אבל למה שואף שתי מינימות ולא נגיד שיהיה יותר יש M השישית זה משהו שהוא נגיד פועל המסר השישי, אז הייתי יכול לצפות שאולי יהיה מקסימום 6 שורשים במקרה הכי גדול. השני עוד שורשים.
You can always like you can go and draw that if you're not sure, like not in the test, but in study for the test, but like it's always going to look the same.
אני מניח שזה כאילו צורה כללית נכונה באופן כללי.
Yeah, but like as I say, you don't have to plot it into test if you don't have to. But you're always going to have the symmetry back it, so at least you know how it's looking like the
שישבור סימטריה או משהו כזה, וזה מספיק מבחינת הסבר שבאמת חזקה ספציפית.
So write it like that. So this is A. So B is so this is we have A of t m to the power 5 plus b m to the power 6 plus c m to the power 8. So the concept is similar. Like it just break break the symmetry. Okay, break the symmetry is not good because the whole point of second order phase transition is that you break the symmetry.
פשוט לא מתקיימת phase transition בסדר 2.
Yeah, so it's break the symmetry in the way that the function not going to be symmetric. So if you're going to look at like below the transition temperature, instead of having like those two basically supposed to be the same height, like minimum point, one of them going to be like that. And then if you go like above the critical point, you're going to have something that like looks like that. So you're just going to go from one minimum to another, which is minimum to another. So this is really like a first order phase transition, second order phase transition. So yeah, so this is also not going to work for us. Okay, so C is so we have F equal to A of t to the power 2. So now we changing the coefficients. M square, B m to the power 4, C m to the power 6.
לא, כי בדבר הזה אותה חיובי.
לא משנה סימן ב-TT.
Right. So the coefficient of the lowest order of the order parameter is not going to change sign when we go below and above the critical temperature because it's square. So again, not working. So the last example is now we have A of t to the power 3. So we have A cube, m to the power 2, B m to the power 8, and C m to the power 18. I'll be sure. So this is going
אמרת ש-A צריך ללכת לפריטים השלישי.
רגע, מה עם B הוא חיובי במעבר פאזה?
Yeah, I think the questions like those are given to be positive. So
Okay.
they should be like part of that. Just don't have the git version.
היה, הגרף הוא בעצם F כפונקציה של M.
F as function of M. Yeah.
רגע, גם B וגם C צריכים להיות חיוביים במעבר פאזה, או שרק B צריך להיות חיובי במעבר פאזה?
In that case, they're just given to be positive, but like, I'm not sure they have to.
שבי חייב.
C לא צריך, יש B, כן.
יש איזה
So-
תנאים, כאילו שאנחנו צריכים שזה חייב יקיים.
Yeah, so I'll just say because everyone's at the same time. So this is, we do have base position because a to the power 3 is going to change sign in the same way that just a going to change sign. So this working in the same way. Yeah, so basically the conditions that we have for a second order phase position is that so the coefficient of the first order of the order parameter have to change sign when we go below and above the critical temperature.
צריך להיות חיובי.
No, it's going to change sign.
זה, אוקיי,
Yeah.
זה כן.
All of the exponents have to be positive. Have to be even. So all of the powers of m.
חוץ מ-H של M, נכון?
Yeah, unless I have except of the one that's multiply the magnetic field. Yeah, this is the point. So this is always going to be good.
אז רגע שנייה, אז כולם זוגיים ורק זה היא זוגיים?
Yeah.
אוקיי.
So
אם
they will have to tell you this is the magnetic field.
אם ה-A של T היה לא באיבר הראשון, כאילו, אלא באיברים
שלישי,
לכאורה B או C.
No, so it have to be in the first one. Like you can have stuff that depends on T basically
עם החזקה
later,
נמוכה.
but yeah, it have to be the lowest order.
בי צריך להיות ללא שינוי סימן, זה הפן השלישי, שהוא באמת חייב להיות בסימן.
Yeah, like yeah, it's basically yeah, but like I never saw a case that's. So within like reasonable examples, those are the conditions.
אני רק להסביר מבחינת שרטוט למה D מתקיים, כאילו, לפני כן להסביר ב-A, B ו-C למה השרטוט כביכול מכשיל את זה, אבל לא הסברת ב-D למה השרטוט כן מתקיים לצורך להגיד את התנאים.
It's in the same way. Like if you have like instead of having like something that go like that, you have something that's go like that. So you have some. If you look at like temperature below the critical temperature, so you have some numbers that multiply m square for specific temperature. And if you go above the critical temperature, you're going to have another number minus now. For example, let's have it's still a number. Like you don't care about like if I multiply this number by like 20 or whatever. Like it's just a number. All I care is the sign for like the way that that thing looks. So,
אוקיי, אבל למה אתה מסביר את זה שיהיה מעבר פאזה? זה שיש שם סימן שלילי, כאילו, לפני כן תראה את כל הערים והגבולות וממש.
yeah, because it's the same. Like the thing that determine how that's going to look is just the sign of that. Like if that sign is positive or if that sign is negative, it's going to choose if it's going to look like that or that. So if you like if you're in temperature above the critical temperature, you need to have something like that. If you're in some below temperature below the critical temperature, you need to have something to look like that. So that's it.
והחזקות הזוגיות האחרות פשוט מחזיקות את זה.
וכשיש H בחזקת M זוגית, אז לא מתקיים מעבר פאזה מסדר שני?
No, I also don't think that's possible. As far as I can think about it.
מה שאלתי, H הוא בחזקה שהיא לא 1?
No, you can have something that's not one. You can have like H multiplied by n to the power of 3 or something like that. That's fine. But just not an even something.
זה יכול להיות H בחזקת M3?
Yeah.
אוקיי.
אבל אם זה M בריבוע או M ברביעית, משהו זוגי, H כאילו H כפול משהו, M בחזקה זוגית, אז זה לא יהיה.
זה ממש שזה לא קיים.
Yeah, I cannot think about like a physical system, but maybe I don't know all of the stuff. Okay, so last question about also phase transition. So this is from 2019. A. Question 2. So here, again, you have like two parts for the question. So we're going to solve the first one, and then we're going to solve the second one. So we have a Hamiltonian of an anti-ferromagnetic system. So we usually work with like ferromagnetic systems, so the opposite. So the Hamiltonian is equal to J, sum of Ij, Sij, Sij plus 1 plus Sij, Si plus 1, J plus H sum of Ij minus 1 I plus J Sij. So J is positive, and well, H is positive too, but it doesn't matter. And the question is, so first part is to find the ground state and the ground state energy. So ground state and E ground state.
ההבדל בין ground state ל-E ground state?
The state and the energy of the state. So for example, for like normal 1D Ising model, the ground state is where all of the spins are heading up. The ground state energy is what you calculate from the Hamiltonian, so like N, like minus NJ for that example.
אבל באנטי-פרומגנט אחד למעלה, אחד למטה.
Yeah, I just explained the difference here. I didn't answer the question.
באנטי-פרומגנט אז J גדול מאפס, בפרומגנט אז J קטן שווה מאפס.
No, we usually have a minus here. So J always larger than, not always, but like J is usually larger than 0 in the questions that we saw. We just usually have like that.
אז בפרומגנט יש מינוס, ו-J גדול שווה מאפס, ואנטי-פרומגנט עם מינוס, אז זה קטן מאפס.
If we had minus, J will have to be smaller than 0. But in that question, yeah, like we just think about it like we want to minimize the energy. So if we have minus and then we have multiplication of the spin, we get less energy if the spins align in the same direction. If we have plus, we want the spins to align in opposite direction. So, you know, you get less energy. So,
וכאשר זה פרומגנטי, אז מעבר פאזה מתקיים כשכולם באותו כיוון, כל הספינים, ובאנטי פרומגנטי זה הפוך, כאילו כשכולם, השכן ליד השני הוא כאילו הפוך לשני.
Yeah, so the way you define the phase transition is that you go from like one value of the order parameter to another value of the order parameter. But we're going to get to that in a second. So just when we so the ground state of the so when we think about anti-ferromagnet, we need all of the spins to be like as different from the neighbors as possible. So if we had like just one dimensional chain, that would be like trivial. We have one up, one down, one up, one down. So we are in two-dimensional system, so it's kind of basically the same, but two-dimensional. So if we have this one spin up, we want all of its neighbors to be down. So this one, this one, this one, this one, right? Because the interaction is with like j+1 and i+1. If we had more interactions, that would be like much more complicated.
אי אפשר לצייר אותם חץ למעלה, חץ למטה, חץ למעלה, חץ למטה, שורה, שורה, כאילו?
Yeah, I'm just showing like each interaction separately. So that's like one interaction term. So this is one spin with 4 neighbors, and for each one of those neighbors, we also have 4 neighbors. So this is going to be like that, that, and so forth. Yeah. This. You understand? So this is the state. And the ground state energy, so we have two parts here. We have the interaction, so we already established how it's going to look. So we basically have two options for the states. So either that or like the opposite, like all of the spin up going to be down and all of the spin down going to be up.
But the magnetic field breaks this.
Exactly. So we have the magnetic field that is for half of the spin going to be down, and half of the spin is going to be up. So the direction, the way that we choose one of those two states is by the direction of the magnetic field. So this is going to like break the degeneracy of the problem. So yeah. So it's made that like that spin field magnetic field up and that spin field magnetic field down. So this is like minus plus.
אפשר עוד פעם להסביר את ה-ground state? איך מצאת אותם?
Yeah, I didn't find the energy. Yeah.
Energy.
So do you agree that we have two possibilities for that state? We either have that state or all of the blue get to be red and all of the red get to be blue. So we have two. So which one of them is it going to be? So we have, in addition to the interaction, we also have the external magnetic field. So the magnetic field is going to be, you see from the way it looks like I plus j going to be like odd and even, depends on the sum. So half of the spin is going to have magnetic field plus and half of them going to be minus. So if, for example, I have like plus minus plus minus plus minus, so that means that this is going to be the thing that breaks the symmetry. So the system we want to choose to align with the direction of the magnetic field. So if I could have either that state or that state, so those two are like equivalent from the interaction point of view. If I had a magnetic field that looked like that, like minus plus minus plus, the system going to choose that direction because it's aligned with the magnetic field. Okay?
פה את אומרת שתקבל יותר אנרגיה כשהם יהיו באותו כיוון של השדה המגנטי.
I'm going to get less energy because you have a less like resistance.
שנייה, אם השדה הזה באותו כיוון של... רגע, איך העניין של הכיוון פה נכנס, של אם או נגד כיוון השדה? כאילו, אם שניהם חיובים זה יצא חיובי, ואם שניהם כאילו שליליים זה יצא חיובי. אז כאילו... הסימן כאילו שמינוס חלק I ועוד J צריך להיות הפוך מהסימן של SI J, כדי שתקבל מינימום אנרגיה. אם באותו כיוון אז זה לא אמור להיות.
אם אתה באותו כיוון זה אומר
Yeah,
שאתה לא
that's why
מתנגד
you
לו.
have the minus.
עוד פעם.
That's why you have the minus. Like because we usually have like we usually just have that. So here you can like take 1 minus up and then say like, oh, like the spin going to, because okay, if we take like the way you can think about it is just like we have a magnetic field that like flip the sign to the system, so we can either define it like that or like that. It doesn't matter because we can always just take minus up.
אז האנרגיה של מצב הסודי תהיה אם זה עם כיוון השדה?
Yeah, basically. Yeah. Like I said, here it's a bit confusing because it depends how you define like that, but usually that's how magnetic field works. So that's how we look at it.
אני עוד כמה שאלות לפנות לעשות.
That's the last one.
התשובה אומר פה למצוא את הגראונד סטייט ואת האנרגיות, אז תשובה לגראונד סטייט של השרטוט זה מספיק.
Yeah, so this is for the ground state, and now let's look at the ground state energy.
תוכלי אולי לבדוק במילים את ה-ground state, איזה נימוק זה נקרא באנגלית?
אני לא בודקת את המלכה, אני לא יודעת מה בדיוק מה...
כן, אבל...
Yeah, that's a very good point. But what I would do, if I would take test in video, I also never did test that it object, I don't know. But what I would do is I would do that, like I would explain like, oh, I have like half of the spin up, half of the spin down, like in like that way, just like just.
Yeah, you can just write Sij equals -1 to the power of I plus j. That's how you set that's the mathematical expression for this.
Okay.
How you can write it?
So you want to write what he said? Okay, can you repeat?
Sij equals -1 to the power I plus j. That's mathematical expression.
אוקיי, אז
Yeah, and then you just flip with by and j, and then the way you.
I ו-J, נראה לי מסך הזה.
Okay, are we all happy? Good. So just the ground state energy so when we're going to have the interaction with the field, like this is the easy one. So everyone are aligned with the magnetic field in like the right direction. So we are going to have like so we're going to have like we have n spin in the system, so we're going to have n spins that align with the field. So n minus multiplied by h.
את השתי
Minus h, and then you have all of the misaligned spins that give you like -1. So you have minus. So each one of the interaction terms will give you 4j. So this is 4j, but that means that you count twice over all of the spins, so you need to divide by 2, multiply by n. So this is overall minus n h minus 2j n.
ה-NH זה רק מעבר של השדה, נכון? ה-NH זה רק מעבר של השדה. כי כל ספין חווה H כאילו?
Yeah, because they're all. So that's energy. The second part asks about the degeneracy, but like we kind of answered that. So it's asked what the degeneracy of the system. So the answer is that there is none. So like 1, because originally we had 2, but because of the magnetic field, we only have 1 possible state for this energy. So G equal 1. And
כלומר, אם לא היה שדה, אז
Yeah, if you don't have a magnetic field, that would be 2. And the last one is to explain whether or not the system undergoes a second order phase transition. So we see that like there is only one possible the order parameter is always, as far as we talk, it's always the average magnetization. So in that case, the only possible minimum is where all of the spins are like misaligned with each other. So the overall magnetization is 0. So the average magnetization is 0.
אבל הולכים פה לפי מה ארגון, לא?
כן.
את צריכה להגיד שהשדה הממוצע הוא 0, ואז...
לא, זה לא פה. פה זה לא...
But no one said that the magnetic field is weak or anything that...
אז מה נשאר ל3?
Yeah, so the answer is not there. There is no final temperature phase transition.
רגע, עוד פעם, אפשר לנמק באמרים מה? או שפה לא?
No, it's not relevant here to begin. Like, okay, even in that case will be a bit more annoying to do because this is like a different system. Technically you can, but in that case it's not relevant because no one told you that H is like is small or anything that we know. We're going to use it in the second part of the question, which is like the more important one, so I want to get to it as fast as possible. So that was the first one.
רגע.
אז בגלל שהמגנטיזציה היא שווה 0, אז הסיכוי ש...
Yes, we only have one possible minimum point. So we can just say like, yeah, that's... We don't have like any reason for simplicity. Okay, so now we have a ferromagneticizing model. So this is... okay, I didn't find my model. So this is minus J sum of Sij, Si plus 1j, Sij with Sij plus 1. So the interaction term is the same interaction term. Plus sum of so we have two terms for the magnetic field. So the first one is epsilon ij, that we're going to write in a second what is it, and hij that is multiplied by delta function of modular function of I with 3 and delta function of modular function of j with 3. And all of that, of course, multiplied by Sij. So the question gives us that epsilon ij is equal plus minus epsilon with equal probability, and hij equal plus minus h with equal probability, where epsilon is much smaller than j, and j is yeah, and j is much smaller than h. So yeah, so someone sent me this question. I don't know if it was
אבל לא אומרים פה שהשדה הוא חלש.
Yeah, so I am not sure if that was like, because that's what is given in the test. So I'm not sure if that's like a mistake because it's a very old, not very old, but a bit old test. No, it's okay. So there is a possibility that that's a mistake. So I'm going to solve both options because I think both are good teaching moments. So let's assume that it's not a mistake. So the question is basically to just explain if you have or not final temperature phase transition. So okay, so case 1, that really h is much larger compared to j. So in that case we have some strong magnetic field in the system. It doesn't matter if it's random, it's still a strong magnetic field. And as far as we know, we don't have any reason to assume that we're going to have a phase transition, because we know that fields tend to interrupt the system. So the important part here is that we have those delta functions with the weird modulo function. So this can be like, this is kind of like a trick. It's kind of, can confuse the student, because you start to calculate like, oh, if I equal that and j equal that, but like that doesn't matter to anything. Like we can just ignore that like altogether. Yeah. So if h is much larger than j, or even if it's the same order of magnitude of j actually, but just because it's given that way, so we're going to take that. So
באופן כללי, אבל מוד I3 זה אומר כאילו שערית חלוקה בשלוש, נכון?
כן.
כלומר, השדה מאוד חזק, לכן הוא בעצם לא יכול לשנות את הפאזה של המערכת. בעצם הפאזה של המערכת לא יכולה להשתנות.
Yeah, so it destroyed the phase transition.
כן, כי זה תופס את המערכת באיזו צורה מסוימת, והם לא יכולים להתהפך, הספין.
Yeah, so you have like, even if it's random, right? Like think about it, you have like all of the spins aligned in the same direction, and then you activate like a very strong magnetic field here and a very strong magnetic field here. So even if they like opposite direction or something, it's still going to probably affect the system. Also we did like the actual derivation when we did the Riemann thing, so you can see there that if you take h to be large, like everything just nothing works. So no phase transition.
אבל זה לפי עם רימן.
לא, חשבתי, זה לא היה לפי.
אוקיי.
Yeah, so this is like, it's in Riemann the way that like we cannot use in Riemann, so we have no reason to assume that we're going to have phase transition. It's kind of like the opposite. If this is a mistake and h is much smaller compared to j, so now supposedly we need to, maybe we do need to look about on the delta function, but it still doesn't matter, because even if we use in Riemann, you see that like h of j is random. It's like half of the time going to be plus and half of the time it's going to be minus. So it doesn't matter if sometimes we multiply it by zero. Like on the spins that you do going to have magnetic field, the average going to be zero. So like the average over hij, it's still going to be zero. Like it doesn't matter if you like remove some of the spins like randomly.
מה המודל עושה? לוקחת את השארית של
Yeah, so you're going to have like 4 modulus v going to be 1.
אבל זה לא מספיק, צריך להסתכל גם על המימד.
אז זה
ואם יש שם תנאי על המימד.
צריך תלת מימדי.
די גדול משתיים, די צריך להיות גדול משתיים.
גדול משתיים.
Yeah, so for d equal to, I don't remember what we agreed.
די גדול משתיים זה
So it's bigger or bigger equal?
גדול, בגדול.
גדול.
Are you sure?
כן.
Yeah.
So if it's larger than 2, you can use it.
העניין עם השווה, הקטן שווה 2, זה היה בלונג ריינג'.
אז אין שם שווה.
פה זה רק גדול משתיים.
גדול או...
רק גדול משתיים, יש מעבר כזה, אם זה קטן משתיים, קטן שווה משתיים, אז אין מעבר כזה. יש לי את זה טוב.
אז קטן שווה ושתיים, אין מעבר.
אין מעבר כזה, הנה נראה. הנה תראי. מה שדיברנו בתיאור.
Yeah, so if it's equal to 2, we use imima.
לא, רשום פה גדול משתיים.
רק כשזה גדול משתיים.
זה מה שאמרנו בתיאור.
משלוש.
כן, משלוש. אולי אני אראה לך משהו נוסף, בלונג ריינג' שם כאן לפני, אז פה באמת זה היה לונג ריינג', אז פה זה היה קטן שווה 2. קטן שווה 2 יש מעבר כזה, אבל פה זה
נכון,
גדול.
באחד מימד, כן.
מה?
באחד מימד.
כאילו יש לך גם ב2. קטן שווה 2, זאת אומרת גם ב2, שני מימדים, יש לך גם מעבר.
Yes, indeed, I need to read my own notes. Okay, the important takeaway from this question is just the part with the magnetic field. So if you have like a magnetic field in the system, like something that is like randomly like uniform distribution, like plus or what or minus 1. So it doesn't matter what we multiply this with, like if it's something that's like, unless it's like going to change like the value of the field, this is still going to be like the same distribution. So the overall magnetic field, the average magnetic field is going to be 0. Therefore, like it doesn't matter in any case what we have here. So just let's remember that.
מה אנחנו עושים עם אפסילון?
Yeah, so epsilon is much smaller, so it's like in that case it doesn't really matter. In that case, it's going to be exactly like HIJ.
אז אנחנו ממניח שהמעבר, המימד פה גדול מ2?
What?
אנחנו ממניח שהמימד כאן הוא גדול מ2?
Yeah, I think this question have some problems actually.
Yes.
Because so like last year me and Ido had discussion about what happened in the equal to. Like this is like he said one thing and I sent him a paper and like it was the whole thing. So like I don't know how he took it in the test. So I'm not sure what happened in that particular test.
אבל יהיה
But like-
עם ריפה ואנטי פרומגנטית ופרומגנטית, נכון?
What?
אני שואל שיהיה על אנטי פרומגנטי ופרומגנטי, זה צריך לדעת.
מה שאמרנו.
You need to know what anti-ferromagnetic and ferromagnetic are. That's it.
אבל זה כן משנה.
But like, yes, someone need to tell you what's the dimension.
פשוט על זה קריטי, נגיד לא יודע אם זה שווה חצי ניקוד, נגיד אם זה היה רק נגיד, אנחנו יודעים שזה עם מימד קטן מ-J, קטן משמעותי מ-J, זה יכול להיות חצי ניקוד משאלה, 16 נקודות, כאילו על דבר כזה. אם זה שתי מימד או שלוש מימד, פתאום על
You
דבר
won't
כזה.
get all of the points to move just
Yeah, like
because.
okay, there are two options. Either the question was not like well defined or something like that, and then it's like it's Ido's fault, and like you're going to get the point, or like it is well defined, and then like someone need to tell you like what's the dimension and like we're not supposed to have like that's the type of mess in the test. Like I typed the test, it's fine. But like yeah, I just wanted to use that as an example. Yeah, I had one more question, but like it's not super important, so like I can put it on the model or something. But like I think I covered more or less what was. Okay. Yeah, I had one more question from Moed Bet of like last year, but like it's not super relevant. Like if someone wants, I can put it on the model.
הראשון כאילו?
Yeah, Moed Bet question.
אבל זה לא קשור.
Question one. It's not that it's not important. It's just less important.
שאלה טכנית. יותר כאילו להביא את הנוסחה של האברס טורטונוביץ' של המעבר שם? או שזה נחשב בתור האינטגרל?
אסור להגיד כלום.
אבל זה חישוב אינטגרל.
As an integral. Like if you can find it in integral book, like I guess it. You can bring the book. I don't know how it works, but like, but basically no. Like technically
אז אסור
no.
ספר אינטגרל.
But no, if you find it in the book, you can bring the book. I don't know if it appears in the book. I never saw the book. I think David Kessler has the book. I see him using it.
אני מאוד בשביל.
יש לי שאלה. שיעורי בית.
Yeah. Yeah, I need to go through that.
תודה רבה.
היה פעם.
מיטב, תוכלי לשלוח?
יש פה את כל האינטגרלים, קצת מצטרפס.
אני כנראה לא
כל הסוגים.
השלטונים הראשונים, כאילו.
כל מה שאפשר לפתור היית רוצה אפשר. אבל לא יודע אם הוא קיים.
ואם זה, אם הבוחן לא מגן, יש אפשרות, כי היה איזה גם משהו בבוחן, שהוא היה איזה ציון, כאילו הוא נתן ציון ולכן זה משנה. ואז מצאתי הוכחה שבטח מה לפני השינוי זה נכון. אז סתם מעניין, ידעתי אם זה יהיה מגן בבוחן?
לא, זה לא יהיה מגן, אבל הבוחן הוא 5 נקודות מהציון הסופי, אז כאילו...
זה איכות בנוסף ל10 של התרגלי בית?
לא, יש 5 נקודות שיעורי בית, 5%